Where'd you get the fur coat, Tony? The judge asked me. I met a guy, I told him. He said he was in love with me. He gave me the coat. A likely story, he said. I said, but it's true, every word of it. I tried to pawn it because I needed the money. Where's the man he has? I don't know, I said. He took a powder, he flew to the moon.
If you love listening to this show, please consider giving a rating and a review on Amazon Alexa or wherever you listen. We want to continue bringing you this amazing content, and part of our ability to do that means that we need a big audience. Now, it may not seem like much, but rating and reviewing the show will help more people find us, just like how you found this show. Simply on any podcast platform, search for our show, scroll down to the bottom, and push 5 stars. It's that easy. Thanks for supporting the show. Today, I'm joined by John Levy, who is the co-founder and CEO of Seeqc. Welcome to the show today.
Thanks very much. And Scott, thanks for having me. And it's a pleasure to speak to somebody who's so well-versed about quantum computing.
So John, you have led Hypres, ePlanet, and other roles, including being a VC and, of course, chairing the investment committee of the Nathan Cummings Foundation, overseeing some $450 million in endowment. How would you characterize the intersection of your multidisciplinary kind of background experience in terms of where you really enjoy and you thrive the most?
That's a great question. Thanks. It's funny. I used to work in a think tank in Silicon Valley called Interval Research, which was funded by Paul Allen. And one of the things that Paul challenged us to do was to invent the next core technologies of the next 20 years. But he wanted them to be done now. And so at that time, and this was in the mid-90s, our idea was to start something, to work on something called computer vision, which was something that very few people had been working on. And so my interest in deep tech, as it's now called, or frontier tech, has gone through, kind of years and years of both running companies, starting companies, and as you say, working as a VC, investing in them. So, I come to quantum computing from having been the chairman of a company called Hypres, which has had its roots at IBM as the superconductive electronics division of that company. And I was chair for, about 8 or 9 years. And about 3 years ago, we ran a strategic planning process where we were trying to understand the best use of this technology, of what we had developed. And most of our work was in superconductive electronics for RF, almost entirely for the US government. And we had been working with IARPA on trying to develop a superconductive exascale computer, classical computer, and realized that there was going to be a strong commercial market for that, and that we could apply this also to running quantum computers so that we could actually work with high-speed classical and quantum computers based on our core technology and our capabilities.
Wow, that's a great starting point. So that brings us to Seeqc. What exactly are you looking to do there to leverage what you just talked about?
Yeah, so it's important to know that we design circuits which are not CMOS. So most everyone in the world that's working on electronics works with CMOS, and that's what Intel does, and TSMC, and AMD, et cetera. We are working with something called single flux quantum technology, SFQ, which is what we developed, the core technology that we developed at Hypres. And we design chips, we manufacture chips. So we have a 9-layer superconductive electronics chip foundry, which is probably the most sophisticated one in the world. And then we figured out how to incorporate those into full systems, to integrate them. Now, at Hypres, we were working on RF systems. But when we started working with IARPA about 4 years ago, partnered with IBM and BBN to develop really high-speed classical computers, we said, well, wait, we could actually develop the same sort of classical co-processing, and then use the same architecture for developing chip scale readout and control of quantum computers, because all of our circuits had to operate, or have to, in 4 degrees Kelvin and below. And whereas for most applications, that kind of packaging presents a challenge, with quantum computers, and particularly superconductive qubit quantum computers, you need that. So essentially, the packaging comes free. We get, superconductive qubits operate between, really say, 10 and 20 millikelvin, and our circuits can operate at that temperature all the way up to around 3 or 4 Kelvin. So we said, let's take advantage of an environment that we know, super, super well, and we would develop chip scale readout and control chips, chip scale co-processors, all made of single flux quantum technology. All are operating at very low temperature, and we do it because those chips don't operate at 2 and 3 and 4 gigahertz. They work at between 10 and 40 gigahertz. They're operating at 3 to 5 orders of magnitude lower power, and they're all digital. And so thinking about that, and thinking about the architecture of what's going on in, let's call it Gen 1 quantum computing, where everything has to go from cold temperature to room temperature back to cold. It's got to go from, analog to digital to analog. You've got RF lines, DC lines, readout and control lines. So you've got interference. Cables, each one of those cables is between $1,000 and $4,000, and you need anywhere between 2 and 4 for every qubit. And most importantly, when you're controlling it with today's technology, which is usually microwaves, you're controlling it with a technology that's inherently highly energetic. So the more microwaves you put into a system to control more qubits, well, in fact, you're adding more energy, which is adding more heat. And heat is the enemy of the stability of the qubits that you have to keep cold at between 10 and 20 millikelvin. So if you think about the analog to digital to analog conversion, all of the complexity of the RF lines, the amplification that's required and everything, and imagine a scenario in which you've gotten rid of all of that. And you've essentially replaced it with a series of SFQ superconductors, chips. Well, you have a very, very different architecture and a different kind of system. And that's what we're doing.
Well, I'm literally getting goosebumps because this is so exciting. I mean, there are some serious limitations with some of the quantum computing approaches, like you're talking about. Yeah. That's very limiting, and I think those limitations are affecting everything from scaling to energy use to the ability to cool itself and maintain its temperature. So the fact that you guys are addressing all these fundamental flaws or challenges in such a way that's so compact and scalable is very, very exciting. But for those listeners that are maybe, a few steps behind kind of what you're referring to, let's just give them a little bit orientation in terms of the different approaches and models that are out there. So if you could talk about quantum gate array, one-way quantum computer, whereas you got adiabatic quantum computers, and then lastly, the topological quantum computer. And where exactly do you guys fall within those approaches?
So here's the thing. Right now, we're developing our own qubits, first off, but we are also sourcing qubits from different places, academic groups, commercial groups, et cetera. And the reason we're doing that is because we think that the approach that we're taking, which is really an architecture, is one that would work with all of those superconductive qubits. So even topological computing, in fact, we recently filed a patent around doing, chip scale digital readout and control of topological computing. But we're working with, with transmons now. We're working with fluxonium qubits. We're working with different designs, because what we're trying to figure out is what's the best kind of qubit design? Is it fixed frequency? Is it tunable, et cetera, for the kind of architecture that we're bringing into play? And so so what we've done effectively is we've built 2-qubit gates. We have them working with transmons, with tunable devices that are operating in kind of the frequencies that people know. And that's kind of our baseline architecture and system. But we are not stopping there, because we think that the idea of using SFQ pulses, of using magnetic flux and flux biasing and all of that gives new degrees of freedom to be able to read out and control qubits. And we're trying to find that kind of perfect match. And so that's part of the work that we're doing.
I love this. To me, it's so fundamental to the science and research and development.
Yeah.
And I love the fact that you guys are looking for the optimal fit. It's a technical way of saying it's kind of a dating, matching type of an approach. You may also like our quarterly Ask Chair Perkins event that brings some of the most notable experts and category-leading startups in their area of sustainability and human survival on Earth and in space. To register, visit askchairperkins.com/events.
The funny thing about it is that a lot of people who look at quantum computing focus on qubits. They think that qubits are the thing. And to me, qubits are sort of like transistors. And early days, in let's call it 1947 to, the mid-50s, transistors were exotic, they were hard to get, they didn't perform terribly well, they were really expensive, et cetera, et cetera. But it took a few years, and then ultimately transistors became a commodity, and there were different kinds of transistors, and you ordered up what you needed for the kind of circuits that you were building. But transistors didn't make computers. You had to get to integrated circuits, you had to get to microprocessors, and you had to get to full systems. And that's what we're working on. It's that, Scott, it's interesting. Think about like 5 years ago, or maybe 7 years ago. And what were the questions people were asking about quantum computers? They wanted to know, could you build one and could it work? Could it run an algorithm? Could it do anything a classical computer couldn't? And the fact is we've answered those questions. Maybe number 3 we haven't answered definitively, but more or less. But the fact is we know we can build them, we know they can run algorithms, and we think they can do things that classical computers can't. Well, now we have a different set of questions. Now the questions are around what are the applications that are high value and that are potentially attainable? What kind of systems do you need to run those? And how are you going to build those systems? And those are the kinds of questions that we're addressing. So we kind of think of it as like sort of a next generation of quantum architecture.
And it's exciting because those types of questions really shows you it's a reflection of where the maturity of the market has come. And I think you guys are really addressing that architectural aspect. I wanted to dig a little bit deeper into the single flux quantum, which is one of our key IP aspects. Can you give us a little bit more of a primer in terms of what is that and why is it so unique?
Yeah. So first off, SFQ, single flux quantum technology, was developed in the late 80s in the former Soviet Union by a couple of guys who came to this country in the early 90s, and we were fortunate enough to have one of them come to Hypres. And in fact, one of my 2 co-founding partners, Oleg Mukhanov, is in fact the co-inventor of SFQ technology. So we have a luminary in our field doing it. Secondly, the idea of SFQ is that we're not dealing with transistors, for example, as switching devices. We're using something called Josephson junctions. And people are used to, it's funny, people, because of qubit structures, are now used to talking about Josephson junctions. We've been talking about them for 20 years, not with qubits, but using them as essentially switches in classical but very fast circuits. So all of our devices are based on that. We're also using different metrology. So we can't just build a Josephson junction and hope it works at ambient temperature. It works in a superconductive mode. So that means that we have to make it out of different materials. So for example, we make circuits out of out of niobium and niobium titanium nitrate, and we use aluminum, insulators, and we use, we're playing around with tantalum and all of that, but we're using these materials because at low temperatures, they superconduct. So what's superconduct mean? It means that you can push current, and it can, through, and it operates as if we're almost like we're in space, we're in a vacuum. There's absolutely no resistance whatsoever. And as I mentioned before, it's super energy efficient, and you can scale it. By the way, the name SEEQ is an acronym for Scalable Energy Efficient Quantum Computing, and that energy efficiency comes from SFQ. So we become kind of the world leader in SFQ design, core technology, and manufacturing. And we've probably made more single flux quantum wafers for national labs and large companies around the world than anyone. In fact, what's right behind me is one of our, is part of our device.
Amazing, amazing. So can you talk about kind of the surround sound to support it at that, I think you mentioned, was it below 3 to 4 degree Kelvin? Aside from the material itself, what is needed to actually keep that superconductive environment steady?
Yeah, so we can work with, it's funny, let's just say that if you don't have to go down to millikelvin, you can deal with off-the-shelf dilution refrigerators or cryo coolers, we would call them, coming from companies like Sumitomo Electric and things like that. Because you have to go down to millikelvin for qubits, it makes these cooling devices far more complex. Well, most companies are dealing only with what's at the very bottom of the dilution refrigerator, which is the coldest part, because everything else happens at ambient temperature. There are a couple of teams that are working with something called cryo-CMOS, but that has its own issues, which we can talk about later if you want. But what we're able to do is to leverage the multi-stage aspect of the dilution refrigerator, because we can have separate circuits operating at different temperatures, and they all have different functions. So for example, we could have a classical coprocessor. A coprocessor just like you'd have in a classical computer, except that ours runs at about 20 to 40 gigahertz. So it's operating at tremendous speed. And we can do that because, again, if you have to keep the qubits cold, you might as well take advantage of all of that cooling capability to run all of these other circuits at other temperatures. And there's lots of complexity in there, because think about it. How do you connect one layer to another? So if something is at, say, 1 or 3, Kelvin, and something's at 20, millikelvin, how do you connect them? Well, nobody's ever really developed a ribbon cable, like a plug-in ribbon cable that you'd buy, in a parts store at ambient temperature. Who's ever built one that's meant to operate at millikelvin? Well, no one. So we're co-inventing that with another company, because we're having to solve these new kinds of problems that nobody's had to deal with before. So there's a lot of invention in ways that you wouldn't actually think. Again, people are focused on qubits. They're not focused on systems.
So as I'm listening, one of the things I think that is, aside from the core architectural approach you guys are taking, is this notion that because you're having to solve some very interesting problems that others haven't faced just yet, there's a growing portfolio of IP that really makes your organization very defensible, but also very valuable as well. Can you talk about that kind of growing war chest of IP?
Yeah, well, first off, we spun out with 40 issued patents, all around our core technology, around SFQ, around design, process, and systems. So that's where we started. But you're right, and one of my frustrations, to be honest, is that we have multiple legal teams helping us on our filing, because it's just incredible invention that's happening all the time. And the real challenge that we have is keeping up with it. And I look at, and I've spoken to, some of the guys up at Zapata, for example, and they've got, in-house legal teams. And I think we're moving in that direction, because we just don't have enough bandwidth for the kind of IP filing based on the level of invention that we're generating. You know, I mean, listen, this is a great problem to have, but it's a real problem.
It's amazing. It really is. You know, to me, what's exciting is really development of an entire new ecosystem. It's not only the architecture, but it's the ecosystem that you guys are building out as well. How do you foresee, you know, for those that are asking kind of the next generation of questions, where do you foresee that your solutions and new portfolio of products that will come out will help to aid in, you know, identifying the kinds of applications and how it can actually really derive benefit from these potential QCs? Don't forget to visit astroperkins.com to register for our next quarterly events. Past and current speakers include Julianne Hough, actress, dancer, and winner of Dancing with the Stars; Damian Vaughn, former NFL player; Neil Gregory, Chief Thought Leadership Officer at the IFC World Bank, and many more. To register, visit astroperkins.com and click on Events.
I've talked a little bit about the core architecture and what our design principles are and kind of what our goals are, but I haven't really talked about how we intend to go to market. So our notion is we are not trying to build a general purpose, you know, fault tolerant quantum computer. I guess we are, you know, in the long term, sure, but that's not our strategy going forward. Our strategy going forward is to build application specific quantum computers, to narrow the problem set as much as we possibly can and narrow the resources that can match to that problem set as much as possible. And because we have this chip boundary where we can, you know, make chips and we can reconfigure things however we want, we can actually work directly with software developers and co-design circuits that they need. And then we give them controls that they would ordinarily not have in kind of a generic full system. So part of the issue for us is working with our customers and trying to really, really narrow down the problem set and not try to, you know, think we're going to do this and this and this and this. Let's just do this one thing. Let's figure out the smallest part of it and let's aim for that. And that's what we're building. That's our first generation product. And we're doing it across a series of verticals.
Yeah, this is really fascinating because if you think about the large kind of the semiconductor giants like the Intels and then Vitas and so forth, for them, you know, to be able to really, you know, churn customized solutions like the ones that you're talking about is very difficult because they're running so many, you know, wafer runs and so forth, and there's just, you know, kind of capex cost infrastructure to it. So you have a very unique advantage in that regard. Can you talk more specifically around the kinds of handful of use cases or applications that are being discussed that you can share? At least give us an idea as to where you guys are kind of potentially narrowing.
Yeah, I mean, you know, the caveat is that we have NDAs with, you know, with everybody to talk specifically about them. So I'm going to talk a little bit generically about some of these things. But you can actually sort of see who's invested in our company and know a little bit about what we're doing. So, you know, Merck, this is Global Merck from Germany, LG from Korea, EQT from Sweden, who are major investors in AstraZeneca. These are all the kinds of companies that care a lot about quantum computing. And what we see, and by the way, it's super interesting to take, you know, look at Merck, for example, who spent 2 years, had a, you know, a working team of 50 people across all divisions of Merck to try to understand how specifically they can play in quantum computing, kind of what their right to play is and what's strategic for them, who they should be partnering with, et cetera. And we got that down, or they got that down to a very, very narrow subset of options and came to us because they saw that we had a path to scalability. Not that we were going to scale, you know, today or tomorrow, or even 3 years from now, but the idea is that they know that the approach that we're building, if we're successful, will match the complexity of the problems they ultimately have in a real world way. But one of the things that people have discovered, and we have spent a lot of time with, is that just because a problem is classically intractable doesn't mean that it's quantumly solvable. And people sort of tend to think that that's the case. And things that even sound like they are quantum in nature, particularly around quantum materials and chemistry, oftentimes turn out not to be solvable with at least algorithms that we have today and that are available to us today. And so one of the things that we're focused on is not only narrowing the problem set, but ensuring that there is an algorithm that can actually address this particular problem. So if we're working in quantum chemistry, for example, we want to make sure that the very thin slice of a problem that we're aiming for is a purely quantum problem solvable by a quantum computer. Because again, people go down, we've seen a lot of kind of dead ends because they're trying to solve what look to be quantum problems, which may be, but they're not solvable by quantum computers that we have today or with algorithms we have today.
So on that note, I just want to be very clear. Are we talking about essentially mathematical proofs, or are we talking about essentially the actual design of the algorithms, the tools, and the approach to actually developing these algorithms?
More of the latter. More of the latter. Because look, we can project what those maybe someone will come up with another kind of an algorithm, QAOA or variation quantum eigensolver, whatever it is that people decide they want to use. We can project that there will be other things in the future, but we're trying to deal with what exists. And I should also say that it's important to note, again, a thing that we're not doing. I mentioned this issue about sourcing qubits. We are not full stack. We're not developing an operating system. Why should we? When Google and IBM and Microsoft are great at that, and Riverlane, one of our partners, has done a great job with that, and others as well. We're not developing applications because there are companies like OneQubit and Zapata and Riverlane and Parity QC who are all wonderful companies, and they're great at it. Let's partner with them. So what we're trying to do is to build a platform that works with a number of verticals, that supports very, very specific algorithms, and that enables software developers, operating system developers to team with us. And again, we can support them in a really unique way, which is why we've attracted nearly all of them.
Yeah. So for those that are listening that may be either developers or maybe CXOs at large enterprises, they're kind of trying to put their arms around this and figuring out how could they potentially work with you and why. What kind of hints would you be able to provide them, given the fact that there are so many NDAs that prevent you from getting into the specifics around applications or use cases?
Well, so one of the things that you have to think about is, imagine for a moment that we were able to give you controls down to the qubit layer. We were able to give you where essentially, because our readout and control circuits are operating so fast, and that we have classical logic that is embedded in the same architecture that can operate at tens of gigahertz. So think about that for a moment, if you will, for quantum error correction, and being able to have access to huge classical processing power operating at amazing speed, very close to where your qubits actually are. Well, that gives you a huge advantage. Or imagine for a moment that you are controlling the timing of quantum reset, and where instead of having to do something where you're going up to ambient temperature and you're converting analog to digital and all that, we're operating literally, I'm not sure if I've really explained it well enough, but our single flux quantum readout and control chips are mounted directly on top of qubits. It's like it is a multi-chip module. So think of it like a little sandwich. They're like this. And the connection is through bumping and capacitance. So we don't actually have to have even cabling, right? We are literally sitting right on top of qubits. And so think about the speed of doing quantum reset, and imagine making that part of the timing of your algorithm. Well, we can give you the control over that timing.
Well, I wish we had more time to explore. Unfortunately, we are completely out of time for today. I've been joined by John Levy, who is the CEO of Seeqc. Thank you for joining today.
Scott, thanks a lot. It was really fun. I enjoyed it and look forward to doing it again.
If you've enjoyed this episode, take a moment to rate our show on any podcast platform that you listen to. Scroll down to the bottom and push 5 stars. It's that easy. And as always, thanks for listening.